In this part of the course, I want to look at a number of patterns that arise when you are writing slightly larger programs, and I want to introduce to you some abstractions, some useful abstractions that arise out of the desire to somehow make these patterns simpler. This is a little bit problematic in an introductory course because these are patterns that arise in real-life programs, but so far we are only at the beginning of our Haskell journey, even though we have been covering quite some ground, but we have mostly been writing rather small programs. So in principle, it's more likely to be appreciated to have such powerful abstractions available if you have been encountering for yourself what happens if you basically suffer from not having them available. If you have been running into situations where you found you had to write a more complicated program than you would have liked to because you didn't have the right abstraction at hand. We have to somehow fast track this by just trying to develop some ad hoc examples, and these will necessarily be a little bit contrived, but hopefully you will be able to understand that this is code that could arise in a similar way in a real life scenario. So the first example that I want to look at arises in the context of an API that uses the maybe type extensively, and we're going to use the standard example that we have been seeing, lookup tables, right, where the lookups can fail. The only slight tweak I want to do, but it doesn't really contribute anything to the example itself, but it is perhaps a good time. We can move from the rather primitive list of pairs lookup tables that we have been using before that are inefficient now to proper lookup tables that are provided by a package. And I think we can afford to do that because we are somewhat more experienced with Haskell now, and we have also in the meantime learned how to depend on other packages. So let me briefly describe my setup for that reason. So I'm in a monad subdirectory now, and if I look, I have been creating a Cabal file for my package, and that Cabal file has been generated with Cabal init again, right? The only difference to before is I have been removing the line about the source directory. I have been changing the exposed module name to monads, and if I don't have the source directory explicitly mentioned, then it defaults to the current directory. So that means I do not have an src subdirectory. Instead, I have monads.hs directly in this directory, and this is the contents of the file at the moment. And then as build depends, I have additionally to base, I have mentioned the containers package. And if we briefly look at package, we see that containers is a package that is available there with quite a few versions. It's a very popular package that defines all sorts of commonly used data structures. In particular, it defines a data structure that is called data.map. And there are two variants of this data structure, and that is data.map.lazy and data.map.strict. And if you remember, our tables, our lookup tables, they're really based on two data types. There is a data type of keys, and there is a data type of values. Now, the implementation strategy of this particular form of key value lookup tables is to internally use a binary search tree, a balanced binary search tree. So that means you have a tree-like structure and everything is properly balanced, and the key is sorted, the tree is sorted on the keys. And that means that lookups and inserts and deletions and all these operations are essentially logarithmic. But it also means that keys have to be evaluated. Right? There is no way that when we insert something into such a finite map that the key could be unevaluated, because they have to be compared with each other. The keys have to be compared with each other to find the right position where something should go inside of this tree. And that means that like whether you are choosing the lazy variant or the strict variant, the keys are always going to be strict, and the structure of the tree is always going to be strict. So we say that these finite maps, they are strict or evaluated in their spine, so basically in the tree structure and in the keys. Whether you're choosing the lazy variant or the strict variant, that only matters for whether you're also going to force the values, because that is flexible. Whether you're saying I'm always artificially trying to evaluate a value that I'm inserting into this finite map, also up to its outermost constructor, then that is what a strict variant does. Or I'm going to not care, and I'm only going to look at the values if I really look at the values via some other piece of code, and then you're using the lazy variant. So we're actually going to use as an example here a map from integers to integers, and there it perfectly makes sense to just keep it strict. So I'm going to use the strict variant of finite maps. And then let's just briefly look at the documentation here. There is a little bit of introductory explanation of what the idea is, but then the core data type here is this map data type that has two parameters, one for the keys and one for the values. And it's an abstract type as far as we are concerned. So even though internally, we can actually click on source here, even though, let's wait a bit, but now it jumps to the right position. Internally, we see this is really a binary search tree type. So we have a tip, a constructor for leaves that has no arguments whatsoever. We have bin, a constructor for nodes, which stores a cached size for that particular subtree, the size just being a type synonym for integers. It stores the key and the value, right? Key and value, and it stores a left subtree and a right subtree. And it makes certain things artificially strict, right? So in particular, the size and the key and the left and the right subtree are made artificially strict. This ensures the strictness in the keys and the spine, and the strictness in the values is implemented via the functions that operate on this. But so basically we have this binary tree-like structure. This unpack pragma is a further instruction to the optimizer in GHC to do something with the size field that we haven't discussed, but you can semantically it doesn't change anything. It's just an internal in-memory representation hint, so you can ignore this for understanding the definition. But you don't even have to understand the definition. I basically just wanted to show to you that despite this whole package being one of the most optimized libraries in the Haskell ecosystem, the actual tree type that is being used is relatively similar to the tree types that we have already been discussing. Right? But you're supposed to interface with these finite maps just through the public interface that is defined by this module and is described in this interface documentation here. And you can see that there are all sorts of type class instances, and then there are all sorts of operations that construct and modify and destruct finite maps. So in particular, we can create an empty finite map, and we can create a single key value binding. So a finite map that has just a single association of one key to one value. And then in particular, we have a function that goes that is one of the functions that we're going to use that goes from our previous relatively unsophisticated representation of key-value associations, namely a list of pairs, into one of these binary search tree-backed key-value associations. And it just takes a list of pairs in one go to such a finite map. It imposes additionally an odd constraint on the keys. That is a necessity of the implementation strategy that is being chosen. If the keys are not comparable, then there is no chance to put them into something like a binary search tree. But it does not really matter how exactly this ordering is defined, as long as it is a total ordering, as long as all elements can be compared in some way. And we won't need very many other functions. So there are quite a few. But the main other function that we're going to use, so here is insertion, by the way, to insert a new key value pair into a finite map, and deletion. But the one that we're really interested in is lookup. So that is the lookup function. And that has just the type that we are expecting. So we take a key, we take a finite map, and we get maybe a value out. And again, we have an OR constraint on the keys, but that is again just coming from the fact that these are binary search tree backed key value pairs, key value tables. There are all sorts of variants of the lookup function as well that we are not going to discuss. But this is the primary function that we are interested in. Okay, so let's go back to our code. Now, I should say cabal REPL here to load my module into GHCI. And I should now be able to say import data.map.strict, because we have declared containers as a dependency of our cabal file, in our cabal file. And then I can reload here, and now I can actually start doing things like asking for the type of lookup, and then I'll immediately see that I'm getting clashes, namely that the prelude lookup function clashes with the data.map.strict lookup function. And the same is going to be the case for quite a few other functions that exists on finite maps, but with different types than functions that exist in the prelude. So what I'm actually going to do is I'm going to import this module in qualified form. And that means that I would have to say explicitly data.map.strict.lookup if I want to use the finite map version of lookup. That is a little bit tedious, so I'm also going to rename the module as to a shorter name. So in this case, I'm just going to choose a capital M. That's a relatively common practice. Some people will also just say map here. That is perhaps a bit more readable. That's a compromise. But in any case, it's very common if you're importing a module qualified to give it a shorter name so that you can refer to it more conveniently. So now I can say m.lookup to refer to the finite map version of lookup, and I can contrast this with the prelude version of lookup, and you can see the differences. So here there is an EQ constraint on the keys, but here there is an OR constraint on the keys, and then the variable names are different. But otherwise, it's a very similar shape of type signature. All right. Good. There is also the observation now that we also have to prefix the type name itself. In order to refer to the finite map type, we now have to write m.map. I'm going to live with that. Some people don't like it, so some people are adopting a scheme where they then additionally import only the type from the module in unqualified form. Then you can refer to the type map in unqualified form, and for any of the operations on that type, you still need to use the m dot. So that is a combination of imports that you also see rather frequently in practice, that you import some types unqualified and then all the operations in qualified form. But I'm just going to stick with the uniform version. Now let's just define an example finite map. And that goes from integers to integers. And I'm going to use the from list function. And then here I'm going to have a list. And I can start with, for example, mapping 1 to 2 and mapping 2 to 4, right, as a starting point. Well, for some reason I have 3 ints here. That is not correct. And now, if I type example in, I see I get the finite map printed back. The show instance of finite map is a bit interesting because it does not show us the internal structure of the finite maps. It does not show us the binary tree structure, simply because that is an implementation detail that we should not be concerned with. Instead, it actually shows the finite map to us in such a way as if it has been constructed using a from list call. For this purpose, it does not matter that it actually has been constructed using a from list call. We could have been defining a finite map in a different way. So for example, there was this singleton function as well, which we can use to create a finite map with just one mapping. So if we go, like say we want to have a singleton finite map that maps 5 to 10, I would still get it printed using such a from list call afterwards. Or if I insert a mapping from 5 to 10 in our example, then our example finite map has 3 mappings, from 1 to 2, from 2 to 4, and from 5 to 10. Then I'm also going to get it printed back using such a from list invocation. So that is just the way that the show instance is implemented for finite maps. And it still kind of satisfies the convention that a show instance should be presented in such a way that it could be used in a Haskell source program in more or less the same form. Here it's not showing the qualified term because there is no way to know in what way we have imported the module. But it's still relatively close to the way it would have to look for Haskell source code. So it would be easy to kind of copy paste into a Haskell program and reuse. Okay, but it does hide the internal representation. So let's make this a little bit larger. So, and I'm going to deliberately follow the convention here. This is to make it easier for us later to see whether things are going in the way that, whether our functions behave in the way that we expect them. I'm going to always map integers here to the same integer multiplied by 2. But I'm not going to include all integers. I'm going to include quite a few, but for example, I'm going to omit 7, and I'm going to omit 9, and then I'm going to perhaps, let's still include 15, and let's include 16, and let's include 20, and let's include 32. And I think that's a good number for the time being. Right, so let's try this again. Let's type in example, and let's try lookup as well. So if we look up 7 in our example, then 7 is not contained in the example, so we should be getting nothing. And if we look up 4 in our example, we should be getting just 8. Right? And that indeed happens. So now, what we're going to do is we are going to write an example function based on this example table. And what is this going to do? This is as I said in the beginning, is going to be a little bit contrived, but it is not dissimilar from the kind of code that you will be getting if you are working with an API in sort of a real application, where there are possibly several different functions that are all returning maybe values. All right, so the task that we're setting ourselves now, right, starting from a given integer, we want to perform 3 successive lookups in our table. And by successive, I mean that the result of one lookup serves as an input for the next. Okay, so as an example, if we start from 4, we would perform a lookup, go to 8. 8, we would perform a lookup with 8 again, we would go to 16, and then with 16 we would perform another lookup and we would go to 32. Right, and then we return the final result incremented by 1. So we do some final computation on the final result. So rather than returning 32, we would return 33 in our example case. Now, of course, any of these lookups can fail because it's a table and not all entries are contained in the table. So we have to say what happens then. If any of the lookups fail, then the whole operation should fail. Right, so this is our informal description of what we want to implement. And in the next step, we're going to try to define a straightforward implementation of this. Okay, and then we are going to observe what is perhaps wrong with it, or not really wrong with it, but at least not ideal with it. And then we're going to try to use the power of abstraction to make it better. That's the plan.